In this video, we continue our discussion of gases, and in particular, we're going to talk about the ideal gas law. So let's think about this word ideal for a minute. There it is. What's an ideal gas? A synonym for ideal might be perfect. And what do we mean by a perfect gas? Well, in this context, a perfect gas or an ideal gas would be one whose particles behave exactly the way we said they would when we talked about the kinetic theory of matter, which some people call the kinetic molecular theory. So in other words, in our so-called ideal gas, we have particles that are so small that we can ignore their volume, or that are so far apart or are moving so fast that they have no interaction with each other at all. Or particles that always move in straight lines, and then when they bump into something, when they collide, they continue to move in different straight lines, but they don't slow down. Real gases, the particles in real gases, don't actually behave exactly this way. And so you say, well, what's the use of having an ideal gas law if there aren't any ideal gases? And the answer is this. The ideal gas law works pretty darn well to explain what real gases are doing. Where it doesn't work so well is when pressures get extremely high, thousands of times the pressure that we experience here at the air pressure that we experience at sea level. Or when temperatures get very, very low, hundreds of degrees below zero, very close to absolute zero. In those extremes of pressure and temperature, the ideal gas law doesn't work very well. But when we're in our lab here at school, or when we are in most situations, most manufacturing situations, where temperatures aren't extremely low and pressures aren't extremely high, the ideal gas law does a very good job of explaining the behavior of real gases. Remember, we talked about four important properties of gases that we're going to pay attention to as we go through our study of gases. The temperature is a measure of how fast the gas particles are moving on average. Volume is the amount of space the particles take up. The pressure is how often those particles collide with the sides of the container they're in. And the number of moles of gas is a way of keeping track of how many gas particles there are. It wasn't very long after Charles and Gay-Lussac stated their laws of relating pressure to temperature or volume to temperature that several scientists, independently of one another, came across this idea, and that is that if we take any gas, the pressure of the gas times the volume divided by its number of moles of particles times its temperature is a constant. It's always the same number. And this is what leads to the ideal gas law. In fact, this is the ideal gas law, which is most often expressed in this way. P times V equals N times R times T. P is pressure, V is volume. N is the variable that's used for the number of moles of gas particles. T is the temperature. It's expressed in Kelvin, as temperature is when we do calculations with gas laws. And R is the letter that's used for this constant value, which is now called the ideal gas constant. So let's think about that ideal gas constant. It turns out that there are many ways, dozens of ways, to express the ideal gas constant, and it depends on what units of measure you use to measure the other four things in the ideal gas equation. So let's look at a couple of examples, and these examples are the values or the expression for the ideal gas constant that we're going to use as we do our work. So one way to express the ideal gas constant is 8.31, that's the number, and here are some units of measure, liters times kilopascals times moles times Kelvin. So we would use this value when our volume was measured in liters, when we had pressure in kilopascals, and we had the number of particles expressed in moles and the temperature in Kelvin. Or here's an alternative way that we might express the ideal gas constant. 0.0821 liters times atmospheres times moles times Kelvin. And we use this for, again, volume in liters and particles in moles and the temperature is in Kelvin, but this time the pressure is in atmospheres. Wait a minute, you say. I thought this was a constant. How come it can be a different number? And the answer is, it's not a different number. It's just a different way of expressing the same value. It's kind of like what you'd say if somebody said, well, how long is something? And one person says, well, it's 12 inches. And another person says, well, it's 1 foot. It's still the same length. It's just expressed in different ways. These are the same value with different units of measure. And the units of measure will help our equation make sense. You'll see that in an example in a minute. So once again, 8.31 with these units, 0.0821 with those units of measure, and there are other ways to express it as well. So here's a situation that somebody might actually run into. How much gas is in one of these cylinders? So we know that a cylinder of gas has to withstand some pressure, so it's usually made of heavy-duty material. It might be made of metal. And even if the gas is highly compressed, there might only be a few grams of gas in there. And so we need a very sensitive scale to tell the difference between the empty cylinder, which is pretty heavy, and the cylinder with gas in it, which is pretty heavy, plus a little bit. And so it's very hard to weigh a cylinder and tell how much gas is in it, because the cylinder just overwhelms the mass of the gas. And we know that we can't count the particles of gas. There are just too many of them. We don't have time to count them, even if we did have a way of counting them one by one. And so, in order to know how much gas, how many gas particles, or what the mass of the gas is in a cylinder, we can use the ideal gas law. So here's a scenario. We have a 12.5 liter cylinder. It contains gas at a pressure of 7.2 atmospheres and a temperature of 295 Kelvin. How many moles of gas are in there? All right, there's our ideal gas law, PV equals nRT. We're interested, in this case, in finding out the number of moles of gas, N, so we can reorganize our equation, rearrange it, to say that N equals pressure times volume over the gas constant times temperature. So let's make our substitutions. There's our equation. Pressure is 7.2 atmospheres. Volume is 12.5 liters. Temperature is 295 Kelvin. And we choose this value for the ideal gas constant because its units of measure match the units of measure that we're using for our other three properties. Notice that we're not going to make substitutions for these things in here. Those are units of measure, and they will help us make sense of our equation. Let's see how. Let's rationalize our units. So here is our expression to help us calculate the number of moles, and we can see that atmospheres in our measurement cancel out atmospheres in the version of the constant that we're using. Liters cancel out liters, Kelvin cancels out Kelvin. We end up with moles in the denominator of the denominator, which means that moles are really over here in the numerator of our overall expression, and we've got some numbers, some arithmetic that we can do to get an answer. Here it is. Turns out we have 3.73 moles of gas in this particular cylinder. If we know what gas it is, we can use the molar mass to find out how many grams we have, and so we now have a way of really measuring how much gas is in our cylinder without really having to measure. So there it is, the ideal gas law, which relates temperature and pressure and volume and the number of particles of the gas, puts them all together into one package and really helps us figure out some things about that gas. Thank you for listening.